Hello everyone, I'm Bin-Xu Wang, a grad student in Neuroscience Department in Washington University in St. Louis. Today I'm talking about my work with my advisor Carlos Pons in the recent ICLR 2021. To start with, recent years we have seen great advances in deep generative models. You can see samples from Big GAN and StelGAN 2 from these 2 years. These models has a generator map, which maps a low-dimensional vector to a high-dimensional image. However, as these models are unsupervised, the structure of their latent space is usually not well understood. So in the work, we want to understand the latent space structure from a geometric perspective. So we formalize the problem as such. Deep generative models parameterize a manifold in the space of images, and like the following. And on the image space, we have a distance, like the perceptual similarity of the image samples. And the generator map can pull that back onto the latent space. So for example, when we have an image distance to capital D, we can define a latent space distance, a lower d. After getting this distance, we can compute the Riemannian metric tensor in the latent space. We find the Riemannian metric tensor is the second-order derivative of the d squared towards the latent vector z. And you can interpret this Hessian or Riemann metric tensor as a local approximation to the distance. And because the quadratic form of this Hessian approximates the d squared locally. So how do we compute this Hessian matrix or Riemann metric tensor? We can first perform just direct second-order auto-differentiation, which is supported in most modern ML frameworks like PyTorch and TensorFlow. Or we can apply Lanczos iterations to Hessian vector product operator to compute the top eigenpairs. We can define the Hessian vector product operator as following. Given a vector, we can compute the directional derivative of the gradient using that vector, and that defines the operator. Or we can use the backward H3P operator, which uses the Jacobian vector product, which is supported by PyTorch and TensorFlow. Next, we can call the Lanczos algorithm in the SciPy. So this method is pretty efficient. For Big GAN, it will find the whole eigen structure and the metric tensors in the minutes. And for Big GAN, it's like 15 seconds. For StelGAN, it's longer. So after getting this metric tensor, what do we do to it? So first idea is to do the eigen decomposition of it. And after getting the eigenvalues and eigenvectors, we find that eigenvalues is effectively the rate of image change along the eigenvector. For example, when we pick a reference image like this dog, and we perturb it along the eigenvectors, and this is perturbing the vector along the first eigendimension, and you go down the spectrum, and here and here, we find that when we traveling along the lower eigenvectors, the image change smaller, and at the bottom eigenvectors, the image change in a more subtle way, like in background or shadings. And this is quantified in this image distance as a function of the latent distance map. This is also true for StelGAN too. So we observe that different parts of the spectrum tend to encode different image transforms. Like top part encodes like large image change like head directions, pose, and the lower spectrum encodes like backgrounds or shadings, furs, and maybe the color of the cat. This anisotropy is observed in most of our GANs, and their eigenvalues usually spans orders of magnitude from 4 to 10 orders of magnitude. And the weight shuffled GANs are less anisotropic, and which means the anisotropy is kind of a feature comes into being by training. So why does not this feature get noticed more often by the community? So we suppose there's an illusion of isotropy with random direction exploration. So when we interpolating the latent space with random vectors, like this sample from isotropic Gaussian, the effective rate of image change, alpha v, will be more concentrated like this orange distributions, comparing to the whole distribution of eigenvalues. So if we really travel on the top eigendimensions or the bottom eigendimensions, image will change at a very fast or very slow speed. But usually when we travel on the random vectors, the image will not change such dramatically. We also prove that the variance of the rate of image change along random directions, the variance of this yellow distribution, is much smaller than the whole variance of all the eigenvalues. And the difference is usually 2 to 3 orders of magnitude. Next, we want to quantify how the metric tensors are related across the space. So after we computed the metric tensor as 2 positions, we apply the eigenstructure at one position to the other one's metric tensor, and then correlate the results. And we find that this metric tensors has similar effect across the space. And as you see here, the correlation is really high. And the directions that induce a large image change at one position also induce a large image change at another location. And this is really consistent across the space. And across 1,000 points in big GAN, the average correlation is 0.94 on the log scale. The Hessian structure, by this means, is semi-global in the latent space. And we can define an average Hessian for each generator. And this is a useful feature for optimization, which we will talk about later. We also find most of the GANs we analyzed exhibit this homogeneous geometry. Although there are some difference in different types of GANs, we find that the big GAN or DC GAN type generator usually have more homogeneous or higher correlation in their matrix tensors, while the style GAN and style GAN 2 space, especially a Z space, has less isotropic or less homogeneous geometry, while the W space has more homogeneous geometry. So we can talk about this difference if you're interested in the Q&A session. So this Hessian consistency is also a feature of the training. We find this consistency is disrupted when we weight shuffle the generators. After this, we are curious how the geometry is built up by the neural network. So we answer this question by investigating the geometry of intermediate layers. We can define their geometry by following. So we can define the L2 distance in the intermediate layers activations, and then pull back that distance to latent space. So we can have a Riemannian metric tensor for each layer. And we also notice that the Hessian for L2 distance is just the Jacobian inner product for a Jacobian from the Z to the activation Y. So the singular vector of the singular values for this J or the eigenvalues for the H signifies the amplification of your change in the latent space to the change in the activations in that layer. So by alignment, we mean how consistent is the amplification in different layers. So we compute the Riemannian matrix tensor at the same Z0 at different layers. And we find that the latent space, the directions that are strongly amplified by earlier layers are still strongly amplified by all other layers. So in that sense, the amplification structure is highly consistent across the layers. And you see this close to one correlation in this structure. So this view has profound implications on how we understand the GANs. The first implication is about non-space. So for example, in big GANs noise space, when we travel from the center along the on really low eigenvectors, we find that the image doesn't change as much, which is expected. And when we apply a lower eigenvectors on different reference points, we find that the image are changing in a subtle way. And so in that sense, this bottom eigenspace is inducing negligible rate of change. So it's kind of a non-space. If we treat this seriously, it has profound implications for our GANs. For example, firstly, the angle in the latent space cannot be treated as a similarity of the image because you can travel a long distance along the non-space, but doesn't really change your image. Secondly, each direction in the latent space is associated with an equivalent subspace of directions. If you just add a direction or add vector in the non-space, the image transform encoded in the direction will not change. So in that sense, the interpolable axis in the latent space is largely non-unique. Third, exploration in the latent space should be directed more in the top eigenspace instead of in the non-space, because that's not meaningful. And finally, the GAN is compressible, and the effective dimensionality of the image manifold is smaller than the dimension of the Z. The second implication is there will be extreme images in top eigenspace. So we observe that the sample noise vectors are approximately the same distance from the origin in the latent space. However, those samples are not equal distance to a center image because of the anisotropy of the map. And if we assume the total homogeneity, then the image space distance could be approximated by this quadratic form. And so you can imagine when your vectors are lies in the top eigenspace, this distance is much, much larger than the average distance. So to translate that into nature language, it just means those vectors create images that are very extreme and unrealistic. So we sample from the part of the noise space that has a high alignment with the top eigenspaces. And you can see that these eigenvectors create highly unrealistic faces in PGGAN and also in StyleGAN 2, although they are kind of the extreme of certain transform like height directions or gender. So in that sense, we kind of identify a way to find some bad examples even for current well-trained GANs. Finally, I'm going to talk about the applications of this geometric knowledge. Firstly, one easy use case of the knowledge is to accelerate optimization. For gradient-based optimization, Adam optimizer is a very common one, and we know it kind of approximates a diagonal Hessians online by adjusting the learning rate of each parameter. As we know, the overall Hessians or Metric Tensor for the latent space, we can use that to rotate the latent space to make the Hessian each point more diagonal. So that may accelerate Adam optimizer. So original Adam work like this, and our rotated one work like this. After the rotation, the Adam optimizer can perform better in some toy problems. And we apply the trick to the real problem of GAN inversion, which minimizes this problem. And we find it actually improves the GAN inversion scores for samples both in big GANs and ImageNet. And you see the fitting of the image becomes much better. And this improvement is quite consistent across many trials. And also the improvement is consistent across 3 GANs and 4 datasets. So using the rotation trick can accelerate the gradient-based optimization. So we want to apply the idea to gradient-free optimization. CMES is a really common one, and it works by sampling and updating a Gaussian. So we can pre-compute the metric tensor and use that to inform this covariance matrix. Original CMES usually samples a spherical Gaussian around each generation. And in our case, we use the Hessian and its eigenstructure to change that exploration. Specifically, we will cut off the informative axis and do not explore on that directions, and scale down the step size on the top eigen directions to avoid overshoot. We find this simple trick will improve the performance of CMES on activation and maximization problems. For these problems, you are maximizing a function on the generated image space. And when this GAN is big GAN, we find that using the Hessian CMES can increase union activation. And use on the FC6 GANs, we do not increase the final activations, but we can still cut down the search dimension from 4,000 to 500 just by cutting the spectrum. And that's really accelerating the search process. Finally, about the interpretation of latent space, we observe that different part of Hessian eigenspace correspond to different transforms. Like in this example, the eigen0 in Stelgan phase datasets correspond to phase direction change. And the change is quite consistent across these 5 examples. And the change should be easy to interpret. So to validate that this is not just observations of our eyes, but it's common to subjects, we conduct Amazon mechanical Turk study. And we show the users these 5 different image transitions created by finding 5 reference images and perturb them along one vector. And subject will answer a series of questions like, do you see any change? Or how much change do you observe? Is there a common change among the 5 transitions? Like in this case, it may be the gender. And how similarity is the change across the 5 rows. And finally, they answer how hard it is to interpret this change. Non-surprisingly, we find in more than 1,000 subjects that our top eigenspace is easier to interpret than the lower eigenspace. And also, the top eigenspace induce a more similar transform among the 5 image reference. Next, we want to see what's the relationship between our interpol axis and all the previous one, because there are 4 to 5 previous works on unsupervised discovery of interpol axis. So firstly, we find that mathematically or geometrically, many methods could be unified through our geometric finding of alignment and homogeneity. So recall that the G, the generator, is just a bunch of layers inputting each other if it is V4 network. And the Jacobian of that is a composition of all the layers Jacobian. So if we have a L2 image distance, then the Hessian is just the inner product of this Jacobian. With some LPIPS image distance, it will add 2 more terms, but that will not affect the Hessian too much. So in 2020 GAN space work, they find that the top PCs of intermediate layers are usually interpretable. And we comment that these top PCs also correspond to the right singular vectors of intermediate layer Jacobian, which correspond to the eigenvectors of the Hessian. Similarly, in the semantic factorization, we find that top singular directions of initial layers are interpretable. And that's also unified by our alignment because those directions are usually also the Hessian's top eigendimensions of the whole image manifolds. In 2018 spectral regularizer, they claim that the top singular vectors of the Jacobians is interpretable, which is in line with our results. So we also compare with another work, the Voynov and Babenko, which use a learning-based approach to solve this problem. If you're interested, you can consult their codes. And we download their axes and project them onto our Hessian eigenbasis computed on their GANs. And we find that the axis they discovered has a high alignment with our top eigenspace. And also it has a better alignment with single axis, and the entropy is lower than controls. Means it's correspond more to single axis instead of mixture of them. And we also know that our method is much faster than their learning-based method. We also project their discovered axis onto our top eigenspace or highly aligned axis. And we find that after projection, they retain their semantics. So we think we can purify the axis discovered in other methods just by projecting them onto our Hessian structure. In more recent Hessian-Penalty work, they also use a learning-based approach, but they are learning a basis to minimize the non-diagonal terms for Hessian. And they use their stochastic estimator. So we do the same analysis and project their axis onto ours and find that their axis has an excellent correspondence to our individual top eigenvectors with like 0.9 or 0.8 correlation. And the annotated axis has high alignment, and we even find some unannotated axes in their basis set. And they also correspond to interpretable axis. So we also note that our method is robust and faster because we do not need learning and training. And their method has to take 40 minutes per epoch and 50 epochs, and ours is 12 seconds for only 10 points and 50 points. So we provide the order for the annotation process to make it more in principle. Finally, we want to comment that there's an nonlinear PCA hypothesis about the generative models. So we observed that different GAN models learn similar semantic axes in their top eigenspace. For example, in the progressive growing GAN or the style GAN or style GAN 2, their top eigen vector is head directions, and second one is kind of face gender. So we hypothesized that maybe the interpretable axis we discovered in the GAN space is not just a feature of the GAN, but it is really learning the major nonlinear axis in the true manifold of all faces. So the interpretable axis is just about the major structure or PCs of the real image manifolds. So by that, I want to conclude my talk and I want to summarize our contribution. So firstly, we propose an architectural agnostic way to measure the geometric structure. And we second, characterize the common geometric features across many generative models like style GAN and big GAN. And we find that the top eigenspaces usually encode interpretable transforms, and also our findings unifies many previous way of unsupervised interpretable axis discovery. And finally, we find the global matrix tensors is useful to accelerate optimizations on the GAN manifold with or without gradient. And I want to thank my advisor, Carlos Pons and Tim Holy. And actually, our lab is moving to Harvard. And also, I'm going to thank my friends and colleagues, Chen Zhengdao, Shen Yunyi, Sun Hao, Kongming Wei, Shao Yuxiu, and Zhang Kainings. And they are really helpful in reading and providing suggestions to our work. And for that, I'm going to Q&A session, and I'm looking forward to questions. Thank you.